Okay, I think everything seems to work fine. We're recording, we're streaming live. Okay, so welcome everyone to our next Tuesday seminars at the Warsaw University Astronomical Observatory. And today our speaker is Aleksandra Hamanowicz. She likes to be called Alex in her American environment. Alex did her undergrad studies at our observatory, so bachelor and master thesis, and then she moved to ESO, to Garching, and she obtained her PhD at Ludwig Maximilian University this year, actually. And she just started her postdoc position at Space Telescope Science Institute in Baltimore. And she is working on quasars and some very interesting stuff she's going to present us, which was part of her thesis, I understand. So, Alex, please.
Thank you very much. Thank you for inviting me and giving me the opportunity to share with you parts of my PhD work. And indeed, what I'm showing you today was one of the projects I was working on while I was in ESO. So most of that work was done while I was still in Germany. The title, MUSE-ALMA Halos, this is the survey which I was part of, and I will show the results of the survey. And then the understanding quasar absorbers in a multi-wavelength survey. There's several words here which I would like to spend a bit more time to explain what I was interested in, why quasar absorbers are interesting and important to study to tackle some questions in the evolution of galaxies. So I will start from a very, very broad picture. We know now through the multiple simulations and observations that throughout the time, the cosmic time, the universe, especially through the dark matter, started to create the structure which we now today know as a cosmic web. So as the dark matter accumulated in forming the dark matter halos, it started also accreting the baryons, which later started to form first stars, galaxies, etc. So with those fibers of dark matter, of course, this accretion goes along those fibers of the cosmic web. And we also expect that many baryons will be trapped somewhere along the way, not only in the halos taking part of the galaxies, but will be somewhere along the lines of the cosmic web. And in fact, when we try to observe and look for this gas everywhere in the universe, we already have hints to see that this gas actually is everywhere all around the galaxies. So on the left, I'm showing you the very deep stack of the observations of the MUSE, of the Hubble Ultra Deep Field with the MUSE Integral Field Unit spectrograph. It's an integration over all of the galaxies between redshift 2 to 4, where we can see the Lyman alpha emission. And these blue blobs is actually the very faint glow of the hydrogen in the Lyman alpha coming from all of the space all around galaxies at those redshifts. So this is one of the observational hints to tell us that indeed this gas is there somewhere in the intergalactic space, how we call it. We also know that this gas comes in different forms and in a different physical state. And I indicated here that typical differentiation of those different phases of gas. We have this, what we call the cold gas, and that would be exactly what we see on the ZIP image here, about 10 to the 4th kelvins, mostly glowing in Lyman alpha, and also some lower ionization ions. Then we have an intermediate, which is the mix of a different ion phases, and then warm hot, which is really, really hot, 10 to the 6, 10 to the 7 Kelvin. And this one works a little bit like the solar corona. It's very diffuse, it's very hot, but the density is very low, which makes it extremely difficult to observe. This warm hot intergalactic medium is believed to actually follow the cosmic web filaments. And I'm showing you here, we expect, based on the simulations mostly, that this is exactly how this intergalactic space is filled with this very high ionization, very hot gas. One of the main drivers to study this kind of this gas outside of the galaxies was the problem of the missing baryons, which we discovered several years ago. If we measure the baryon density expected from the cosmic microwave background and compare it to all of the baryons we can count in the galaxies, so the stars, the ISM, the gas in between galaxy clusters, etc., and also all of the gas which we already measured somehow in the intergalactic medium, we are still coming short. About 1/3 of all of the mass density is missing. So we don't really know where those baryons are hiding. And again, this very, very hot, very difficult to observe warm, hot intergalactic medium is the best candidate to be the reservoir of those baryons, which we still can account for. That's why we are looking forward to the breakthrough in observations in X-rays, which would be the cosmic mission Athena, the space telescope, which will be the first integral field unit X-ray observatory, which will hopefully help us map the emission or also absorption coming from this very hot gas in the warm hot intergalactic medium. Maybe a quick definition of what integral field unit spectrograph is, because I'll be talking about it later quite a lot when I'll be talking about the observations with MUSE. Is that it's like a combination of an imager and spectrograph, where we have a wide field, we observed quite wide field on the sky, and then each pixel is a spectrum. This quite revolutionized many observations in many science cases when we can have those two informations simultaneously. And for the X-rays, this will be the first time we're going to do that with the Athena mission. So that was the one thing. We don't know where some of the baryons are, so that's why we have to try and find them in this intergalactic medium. But then if we try to look into global properties of gas and star formation in the universe, we find another puzzle. If we look here on the left, there is the star formation history plot when we show the global star formation rate in all of the galaxies at some redshift versus the redshift of the age of the universe. We now know that at the very beginning, of course, the star formation was rising slowly, and then the peak of the star formation in the universe was around redshift 2. That's where most of the stars were formed, and most the galaxies where most of them were basically starbursting. And since then, the universe falls down in the rate of the star formation, and up to today, some people call it even that our universe as general is quenching. And we don't really understand what drives this change on the star formation rate in the galaxies. And one of the ideas would be to compare this rate of star formation with the amount of available gas for galaxies to use for the star formation. To form new stars, there must be enough gas in the interstellar medium of the galaxy, and not only just the gas, it must be in a certain phase, the molecular phase. So there are multiple studies already trying to calculate how much of that gas in total in the universe was available throughout the cosmic time. Then when we look into, for example, the most abundant element, which is the hydrogen in its neutral form, and we try to see how the global density of the hydrogen is changing with time, we will see that the evolution is very smooth, and it doesn't really change much with cosmic time. Here is the redshift, and here is the density of the neutral gas. And in this inset here, we can see the buildup of mass. Here we have in the green, again, the gas, while in the reddish, we have stars. And at some point, there are many more stars, and actually we see the hydrogen to be. So there is still something going on here, and we still don't understand how the star formation in the universe was driven. That's why we're still trying to understand how much the gas there is available for galaxies, not only in their interstellar mediums, but also outside in the intergalactic medium. So I was saying about those main kind of questions where this intergalactic gas can try to play the key role. But how we can observe this? I already mentioned that observing it in emission is a very big challenge. And actually nowadays, with all of the instrumentation which we have available, it's basically impossible to detect an emission from this intergalactic medium gas outside the galaxies. We have only several cases of stacked images, as I showed you before, or around the quasars, which are very strong ionization sources. But around the typical star-forming galaxies, it is right now basically impossible. So we have to use different techniques. And here came the quasar absorbers. So the idea is pretty simple. Instead of trying to look for a very faint surface brightness of the gas, we can look for a distant background sources, bright sources, in which spectra, there will be the imprint in form of the absorption line from the material being somewhere in between us and that source. The best for that purpose turn to be quasars. There are several reasons. One is that we can find them on a very different redshift, so that allows us to probe this intergalactic gas at the different cosmic epochs. On the other hand, they are basically point-like sources and they are extremely bright, which gives the fantastic background for later to see the absorption. As we can see here, there are multiple different absorbers we expect. We know the Lyman alpha forest, quite a popular type of absorption, where especially in the high redshift quasars, we can see a lot of absorption coming from hydrogen in the early epochs. But apart from that, we can also expect the metal absorption lines, which come from already enriched material into intergalactic medium and can tell us a lot about the properties of the gas, not only in a hydrogen form, but also in terms of its metallicity. And I'll come back to that a bit later. One important definition, which I might be using a lot later, is the impact parameter. It can be a bit confusing. The impact parameter is the measurement of the distance from the galaxy at which redshift we see an absorber, and projected at the redshift of the galaxy to the sightline in which we see the absorption. So the projected position of the quasar at the redshift of the absorber, and we are usually talking about it in kiloparsecs. So we can think about it as the distance from the center of the galaxy to its halo where we see the gas. So I mentioned already before a bit about those different phases in terms of temperature of the gas which we are seeing. And what comes with that is that there's a number of different species, ion species, which we can use to try to probe the phase in which the gas is in. This is quite a complicated plot, but the few things which I would like you to focus on is that, first of all, here it's just showing the physical space and the physical phase in which gas can be in terms of density and temperature, and different ions which we can use to probe the gas being in this particular physical space. So neutral gas will be low ionization or not ionized ions and hydrogen. And then we can go through the intermediate and slightly higher ionization state elements up to as high as oxygen 6 or even 7 or 8, while we are talking here about the particles which are already forming this wormhole intergalactic medium. And this is the phase when we are observing them mostly in X-ray. So when we are talking about the quasar absorbers, traditionally we are differentiating between two types. One of the type will be hydrogen absorption, which of course, since hydrogen is the most abundant element in the universe, the hydrogen absorbers are the most common, and we expect the intergalactic medium to be dominated by hydrogen. Obviously the hydrogen absorbers seem to be the most straightforward and the first thing to look at when we are trying to understand this gas in the intergalactic medium. Again, a complicated plot. Let's look at the left part of that plot, and in the center is a halo from hydrodynamical simulations foggy, which is focusing mostly on this gas in the intergalactic medium. And the colors correspond to different density of the gas. So if we now go very close to the galaxy disk, very in the inside where we have a green, that corresponds to the green in those other two plots. These are the hydrogen on the highest column densities, 10 to 20.7, which we call damped Lyman alpha absorbers. This naming scheme is not very physical. It just differentiates between the different densities of the gas, but I guess the DLAs or the damped Lyman alpha absorbers is something which we hear about sometimes. And this we expect the highest column density of hydrogen, which we expect to be very close to the galaxy. So in terms of the impact parameter, not further than about 10 or 15 kiloparsecs from the actual disk of the galaxy. If we go further, then the density starts to fall down, and we start to see the sub-DLAs and then Lyman limit systems, and we are falling down to the 10 to the 18th in terms of the density of the hydrogen. These are quite important numbers, which we are using later to differentiate between the different kinds of absorbers. Also, what comes with those densities is the state of the gas. In this damped Lyman alpha systems, very high density, we are seeing mostly neutral gas. So you also would expect, if there are any metal lines, to be also low ionization. Then sub-DLAs in those intermediate density range where we have partially ionized, and the Lyman limit systems below 10 to the 19th, 10 to the 18th, that's already ionized gas in which we also can look for other ionized elements. So this is what I'm showing here are insets from the simulations from Foggy and from Illustris. However, if we look at the plot here, which is marked with E, when we have a column density of the hydrogen versus the impact parameter, we see, as I already described in a bit, that we would expect the hydrogen column density to drop the further we go away from the galaxy. And we actually observe this. And here we have the observations of the multiple different absorbers from COS Halos project, which was one of the main observational projects trying to understand the quasar absorbers. And indeed, the further we are from the galaxy, the lower column density in hydrogen we are observing. So this was about the hydrogen. So we can also try to look for metal absorbers, and there are several ion species, which we are like in particular because they are easy to detect. And if we are talking about the neutral gas or low ionization state gas, the two doublets which we are always hunting for are magnesium-2 and carbon-4. Because of their different strength of the doublet lines, they make it very easy to identify in the forest of all of the lines which you can see in the quasar spectra. Because they are rather low ionization, well, carbon-4 is this intermediate phase, but magnesium-2 is definitely just like this very dense hydrogen neutral gas. We also, from the simulations here, again, I'm showing the inset from one of the galaxies simulated by the foggy hydrodynamical simulations. We can see that this gas in magnesium-2 is very clumpy, and it shows up in this multiple streams, clumps, and small clouds, which makes it even more harder for us to detect because it's not isotropically distributed all over the galaxies. So we have to be lucky enough to have a sightline going through one of those streams or clumps. On the right, I'm showing you the observations of our absorbers. Here is the magnesium-2 and also iron-2, which also is a good representation of the neutral gas. I'm showing you here two completely different cases in which how the absorption line profiles can look like. On the top, we have a very simple system when there are only 3 well-defined components, while on the bottom, we can see the absorption profile, which is very complicated and have multiple components, which also can tell us something about the kinematics and the clumpiness of the medium which we are looking at. Already that gives us several informations. We can measure how much of those ions are in a gas and try to understand what is the metallicity of the gas which we are seeing. And also through studying the kinematics, we can try to understand how clumpy is the system and what is it comparable to what we see in a simulation, or maybe which part of this very sophisticated complicated halo we are actually seeing. So when I'm talking about the magnesium 2, I have to show another typical plots for the quasar absorber studies. When we are comparing the distance from the galaxy, again, the impact parameter here on the x-axis, with the strength of the magnesium 2 absorption line here on the y-axis, here's the equivalent width. And there is a little bit complicated correlation between those functions, showing that usually we are expecting those magnesium 2 absorbers to be in the rather narrow range of impact parameters between 10 and 100 kiloparsecs to be rather strong. And then suddenly there is a drop when we are going further away from the galaxy, which quite nicely goes together with this simulated halo when we see that, of course, the density of the gas is very strong, very close to the galaxy, and further we go, the density drops. But also another thing is that we do not expect any very faint absorbers when we are very close to the galaxy. So that also shows that there is a very strong gradient in terms of the neutral gas around galaxies. So I was talking a lot about these, the gas around galaxies, and I'm talking repetitively about the impact parameter and galaxy. So I think it's a high time to introduce not only to the quasar absorbers another definition, which is the circum-galactic medium. And it's the arena in which all of the gas flows in and out of galaxies are actually happening. The circum-galactic medium is where we actually expect the quasar absorbers to originate from, especially the metal ones, which we expect will be enriched by the material formed already in the ISM of those galaxies. Usually we talk about the circum-galactic medium to be more or less the virial radius from the galaxy, which for the Milky Way-like object is 300 kiloparsecs. And as I mentioned, this is the arena where all of the gas flows and gas recyclings takes place, which we called the cycle of baryons. So we know that for galaxies to keep forming stars, we need to provide more and more fuel, which is the gas, to replenish the reservoir of gas which was already converted into stars. Hence, the galaxies are not isolated. They keep accreting material from outside, which then is transformed into the ISM, cools down, transfers into molecular gas, and starts forming stars. However, the star formation triggers the feedback processes, which in turn expel the gas away from the galaxy again. Is it either through the very strong stellar winds from the young OB stars, or already enriched in more metal-rich material being expelled through the supernovae, which are main driver of the galactic winds. Some of that material can be accelerated so fast to get away from the system altogether, but most of it will fall back down in the form of the galactic fountain, as we call it, and then reach the ISM even further. So this cycle of baryons, like a cycle of water, we see that we have accretion of the gas from outside, from the intergalactic medium, which we expect to be rather metal poor. And then while it gets processed through the stars in the interstellar medium of the galaxy, can get expelled and reach again the circumgalactic medium, and then fall back onto the galaxy, and this circle starts again. So here we can see that studying the processes happening in the circumgalactic medium can have a very important, can be very important for understanding some of the questions in the galaxy evolution we are trying to tackle, which is most of them is the quenching. We are not only interested in why the whole universe quench, but what are the processes which actually force galaxies to stop forming stars, and how much this inflow and outflow of material, how much role this plays. And then those feedback mechanisms, which I mentioned, are also still very poorly understood. How much mass there is actually expelled and how much mass is actually accreted. These are still the questions we are trying to answer. All right, so as I was saying about those gas flows, more theoretically, it looks very beautiful, but when we would like to observe it and try to understand what we are actually seeing, it starts to be very tricky. It's very difficult to differentiate between what is actually inflowing gas and what is unflowing gas, and how much there is it and how to measure it proves to be a very difficult question. So one of the approaches which we are trying to see is, as I already mentioned before, we expect inflows to be rather metal poor because this is mostly the material from intergalactic medium, which was not processed through the many stars yet. While the outflows would be metal rich because already that material was enriched by the supernovae into the interstellar medium of the galaxy. And there are some observational evidence that this actually can be used as a differentiation between those gas flows. Here I'm showing you the histogram of the metallicities from the several quasar absorbers. It's actually 82 coming into here. And there is a potential bimodality seen here, which would suggest that indeed when we observe different absorbers through their metallicity, we can try to disentangle what is this pristine inflowing gas, while to this enriched inflowing gas, but outflowing gas. But here we are talking about the general population of quasar absorbers. How we can look at the single galaxy and try to say, oh, this one actually is expelling the material and this one is getting it in. So the other idea was that, as I showed earlier on this picture of the circumgalactic medium, we expect those gas flows to happen actually in a particular part of the galaxy. So we would expect that the inflows would come along the disk and form this kind of warped disk, and with the accretion going along more and more onto the disk and the spiral, along the spiral arms of the galaxy, so that we would say that we expect those the accretion to happen very close to the galaxy disk. We measure this with what we call the azimuthal angle, where the 0 is along the disk and the 90 degrees would be perpendicular to the disk. So below 45 degrees, this is where we would expect to have the inflows. Then we would expect outflows to be in the form of those biconical galaxy wind coming out perpendicular to the disk. So hence, maybe looking by the metallicity of the absorbers in respect to this geometrical position, that could be something to differentiate. Unfortunately, as I can show you here, especially the measurements of the azimuthal angle are still very challenging. Most of those galaxies we are talking about are very tiny and are barely resolved even by the HST or the ground-based big telescopes. And it's very hard to measure where exactly the sightline is versus the position of the galaxy. So there is, right now, we do not see any evidence that this azimuthal angle can be useful. However, simulations tells us that that's actually should be the main differentiation between those two scenarios. All right, so the quasar absorbers in the circumgalactic medium, inflows, outflows of the galaxies. These are all of the interesting questions, which I'm also very interested in to answer. So another question will be then, if I look in the distant quasar and I see some absorption lines, how I actually know which galaxy that gas belongs to? And this is one of the other challenges which we are trying to understand and tackle in our studies, because we now know hundreds of thousands of absorbers basically, but only a handful of them has galaxies which are identified as being the host galaxies of that. So in the next part of my talk, I would like to talk to you more about my work and trying to understand how to find those associated galaxies what are the properties of those galaxies, and can we link them somehow to what we see in a gas, in absorbing gas? Also, can we see some interaction between the galaxy and this gas? Just as I told you before, trying to differentiate between different gas flows, but maybe try to understand some influence of the star formation processes in the galaxy if we see a gas which is entering or exiting its ISM. So that's where MUSE-ALMA Halos come in, our multi-wavelength survey of quasar absorbers, which, as I mentioned, the main scope is to not to measure the properties of the quasar absorbers themselves, but link them to the properties of the galaxies. We are targeting mostly low redshift absorbers, as we call it, below redshift 1.4. This should be all of the galaxies and absorbers which already are in this more quenched universe, so not dominated by mergers and starburst activity of galaxies, so can shed some light into how galaxies keep their star formation going, even though the whole universe looks like it's going to quench. Then it's the multi-wavelength survey consists of several observations. There is a MUSE integral field unit spectrograph. We have multiple quasar fields which we have observed with MUSE. Some of them have also ALMA observations to trace the molecular gas. I'll tell a few more words about that later. All of the quasars have high resolution UV spectroscopy, both from the ground, like with UVES, and from HST, to measure all of the profiles of the absorption lines. And then we also have the HST imaging, which proves very helpful to identifying very faint sources and very faint galaxies. So all of that is a lot of data, the different kinds of data, which we are trying to put together to paint the picture of what is actually happening in a circum-galactic medium of the star-forming galaxies and redshift below 1. We are targeting the fields which of the quasars which already we know that have the absorber. However, we do not rest there. That's why we have the UV spectroscopy to come back to this quasar spectra and identify all of the both magnesium 2 or carbon 4 hydrogen absorbers that we can then look for the host galaxies later in the MUSE data. So this is the illustration how the multi-wavelength data set look like. Here again, we can see here the MUSE view over one of the quasar fields, quasars in the center. And immediately you can see that we had 3 absorbers in this field at different redshifts, showing here with different colors. And different colors show you the galaxies which we found associated with those absorbers. The same here on the right with the HST observations. Already you can see how much better the resolution is and helps us to disentangle some of the objects. Integral field unit spectrograph, as I mentioned, is bringing you the spectrum of each of the pixels of the image. And here is the integrated spectrum of some of the galaxies from this field, one of the galaxies of this field, and corresponding quasar absorption profile, which is the gas which we believe belongs to this galaxy. This particular case is very interesting because already we can see very interesting shape of those galaxies in the MUSE, but Hubble shows that these are 2 objects most likely merging, and they are very close to the quasar sightline. So we are probing most likely the very interesting environment here, and that reflects itself in the shape of the quasar absorber, where we have a very complicated profile, which maybe potentially some of those comes from some interaction, the gas being expelled due to the interaction between those 2 objects. Here on the left, we are showing also the contours from the molecular gas measurements from ALMA. This is in green. We are one of the first groups which are also looking at the molecular gas in terms of the galaxies connected to the absorbers to try to understand what is the actual content of molecular gas in those galaxies, how that relates to the gas which we can see in their circum-galactic medium, and how that impacts their star formation rates, which is quite a new angle to look at this problem. And to follow that a bit later, we already had some interesting discoveries. Here, I'm showing you on the bottom that two snapshot of our very rich group of galaxies, which we observed with both MUSE and ALMA. And in MUSE, we are detecting about 20 something galaxies connected to that group. Maybe not all of them are marked here. Here is we are showing the pseudo narrow filter mode around the oxygen line, but some of them have only been detected in continuum. While if we look at exactly the same field with ALMA and targeting one of the molecular gas lines, the CO1 to 0 line, we'll see the three most massive galaxies very brightly shining indicating they have a high reservoirs of the molecular gas. And I think that was one of the interesting highlights of this work, was that the molecular gas was only detected in those most massive galaxies, and the reservoirs were very, very high. However, the star formation rates were very, very low. And since we are talking about the objects in a very rich group of galaxies, that shows that we might see some effects of the interactions between the group members. We are suppressing the star formation, actually. That also raises the question, what we actually are seeing when we are looking at quasar absorber and their galaxies. Are we probing objects which are maybe interacting a lot and are actually quenching because there is a lot of gas in between them? Or is that gas actually keep fueling the star formation of those objects? So all of those questions are very difficult to answer because all of those informations are very entangled. However, we keep observing many, many more galaxy fields to try to tackle this problem. So I mostly said that we are looking at the look for the galaxies looking in MUSE, but you also can just point ALMA and try to see if you can detect them in the first place in molecular gas. And our group also did this kind of study, and we indeed detected several galaxies first in ALMA and then follow it up with MUSE. So you can go both ways, tackling the search for the galaxies. Another thing which is very important by using MUSE is the fact that we expect some of the galaxies to be really, really close to the quasar sightline. Sorry. Which means that some of those galaxies can be hidden under the quasar PSF. And here we have two examples from my sample of galaxies when indeed the galaxies were very, very close and normally would be hidden under quasar PSF, and you can hardly see them here in the MUSE, even though the quasar, I tried to remove it a bit. We detected them thanks to their emission lines, the O2 emission lines, which were seen on top of the spectrum of the quasar. If you go to Hubble Space Telescope observations, especially in this case, we can see that there's indeed a galaxy very, very close to the quasar. So MUSE helps us very easily to detect those objects, even though they're embedded under the PSF of the quasar, which makes it much easier than to remove whole PSF in 2D. We can just do that in the spectral space. So main highlight from our studies so far, I was working mostly on the subset of our fields which we have observed. So there are 5 quasar fields in which I had 14 absorbers, for which I identified 43 galaxies which can be associated with those absorbers. That makes it more than 2 galaxies per object. And indeed, we are seeing the range of possibilities. We have one absorber for which we don't see a galaxy. We have several single pairs, galaxy and quasar, and then the majority has at least 2 galaxies which can be associated. Why is that an important finding? Well, in the classical view of the Circum-Galactic Medium and its relation with the quasar absorber, we usually were thinking of it as a single massive galaxy which Circum-Galactic Medium we observe, and a lot of those gas flows cause the quasar absorbers. So usually we will be satisfied with having one galaxy connected to the absorber. Here, thanks to the wide field of view with MUSE, we can actually try and see if this classical view is correct. And as I'm showing here, in most cases, actually it's not, because we are finding multiple galaxies. that raises the question whether we are biasing ourselves against some systems in which, like maybe interacting systems, which the gas is expelled and then is much easier to detect in the form of the absorber. So this is something we have to understand with a bigger sample, and hopefully that is coming later. I showed you in the very beginning those two classical plots which we are looking at when the in terms of quasar absorbers. One is looking at the hydrogen, especially at the column density of the hydrogen versus the impact parameter, so the distance from the galaxy. Here, since we are now talking about the groups of galaxies, the view starts to be a bit more hazy because I don't know which galaxy of the group is actually the one which is responsible for the gas in absorption. Yet, even if we plot all of them, still we see the same relation that the further we go from the galaxy, the lower the column density we are probing. We do not see usually any galaxies very close to the any absorber very close to the galaxy if we are talking about the low column density in hydrogen. Similarly, if you look at the magnesium 2 and we look at the metal strength, we also fall very well within the space of the typical absorber. So even though that we are seeing groups and we are trying to treat them as a whole and do not point into the particular object to be responsible for the absorption, we are still falling very well with the canonical relations. So that makes it even harder because we cannot say that some of those galaxies are not connected to the absorption based on those relations. So probably we have to look in a slightly different angle, try to tackle maybe the problem kinematically. Some of those quasar absorbers have very complicated kinematics, and maybe this multi-component profiles can help us understand which parts of the absorption comes from maybe which galaxy. I mentioned trying to disentangle between inflows and unflows. So obviously we also try to see if the metallicity can tell us something about whether the gas is inflowing or outflowing. However, we do not see any relation, neither if you look at the metallicity of the galaxies, here the emission metallicity versus the absorption metallicity. There's no relation indicating that some of the gas can be inflowing or outflowing, so it's higher or lower metallicity. Neither if you look at the metallicity gradient, so there's the difference between the absorption and emission, so different between the quasar absorber and the galaxy, and we look at within the impact parameter, again, we do not see any relation. So based on the metallicity, we could not say anything about whether we are seeing gas inflowing or outflowing, or whether we can pinpoint the galaxy which actually is connected with the gas within absorption. So there are even more questions than answers, but I guess this is very exciting. And we are trying to expand now our survey into multiple more quasar fields to try to have better statistics, because as I said, I was working on 14 absorbers. If we talk about something like 100, then we may start to see better relations in all of those properties, which will help us to understand where the gas which we see in absorption originates from. Is it intergroup medium, or is it something connected to the particle one galaxy, or the interaction between galaxies? I mentioned something about the kinematics, and here I show you the kinematic maps of the galaxies in an ionized gas and a molecular gas, and we can try to connect those kinematic features to what we are seeing in the absorption of the gas. That will be the next step to try to disentangle this complicated image. And then all of those galaxies will have measured masses through the multi-band photometry, which we have observations running on the Hubble Space Telescope. So there's many more to come. We are also writing right now the proposal for the survey for Forwardmost to gather even more information and even more absorbers and their host galaxies to try to understand how the gas connects with the galaxies in lower redshift. Just to finish up, I would like to say a few words about what's the future for me also, because I'm still connected to that project, but I'm moving a bit more closer in redshift, and I'm working right now on the slightly different aspects of the gas and dust. One question is, when I was talking about those galaxies and the origin of the gas, the question may be maybe some of the gas which we are seeing are actually very high gas-rich satellites of those objects. And we have an observations of the several Milky Way-like analogs with their satellite systems and several quasar sightlines going through those systems to try to see if we can link some of the gas kinematics and properties with actually the properties of the satellites, which in a higher redshift you would obviously not see, but they still could be prominent in the form of these quasar absorbers. Another thing which I didn't touch at all is the dust. And the formation of the dust, and also it has very strong connotation with the metallicity which we are measuring. Because right now, when we are talking about metallicity, we are mostly talking about what we understand about depletion of the metals into dust in the Milky Way-like environments. However, when we are talking about quasar absorbers, these metallicities are much lower than what are in the ISM of our own galaxy. So in the second project, Metal Z, I'm working on measuring the dust depletion into low metallicity environments in some dwarfs in local group to try then to make the corrections to all of the measurements which we are making, and then trace back how the metallicity of the gas in general in the universe changed with time. So just to summarize, I talked today a bit about the Circum-Galactic Medium, which is an important arena of the gas flows, which play a very important role in the evolution of galaxies and sustaining the star formation. Even though this gas is very faint, we can study it through the quasar absorbers. We are tracing this gas in a different ionization state, different temperatures, metallicities, and all of those quantities can help us understand what the physical state the gas is in, and then we can try to link those measurements to the properties of the galaxies themselves. And that's what we are doing in the MUSE-ALMA Halos in the low redshift multi-wavelength study, where we are trying to exactly find galaxies connected with the quasar absorbers and try to understand how the two interact with each other. Thank you very much. And I'll end here and take questions.
Okay, thank you very much, Alex, for this talk. Now we can have some questions. If you want to ask a question, please raise your hand, either blue. Yeah, exactly like Pavel just did. Pavel, please.
Hi, Alex.
Hello.
Very nice talk. I have a question on the metallicity distribution you have shown.
Mm-hmm.
Could you go back to this bimodal distribution?
Yes. Okay, wait. Give me a second. That's here. Yes.
Yeah, this one. And there was also one other plot on the right side. Yeah, that's one. What I see here is quite big uncertainty in metallicity determinations, in metallicity values. And my question is, how many lines do you use to determine the metallicity, the abundances of separate species?
This is a very good question, and this is something which we are really tackling with. So depending on the actual metallicity which we are talking about, we can also expect different lines. Usually the main line we are using for measuring metallicity is iron. Mm-hmm. But of course, the more, the better. I do not know, this is not my work here, which I'm citing, so I'm not sure exactly how many lines they have, but in my metallicity measurements, I try to have at least 3 different ions which went into the metallicity measurements. So I'll be
different ions of different metals, not only irons.
Yes, so I would get iron and I would get magnesium. Yeah, but in terms of the for the single ion, that also depends. For iron, we usually have at least 2 lines which we can measure. Mm-hmm, mm-hmm, mm-hmm. So yeah, it depends really on the observations, of course.
Yeah, and I suspect that in quasar spectra there is no too many metallic lines, right?
That really depends.
Good to study.
Yeah, it really depends, because some of them can be saturated and then we are done. You can't really measure them. Or depends what is the wavelength range you are probing. So there are many, many things which are coming into this. And then again, if we have a low metallicity gas which you are probing, that there are not many lines to start with. So yeah, that's the problem. Yeah.
Okay, thank you.
Any more questions, please? Michał, please.
I have a question about the absorbers which are in groups. So most of the absorbers are in groups. Does it mean that most of the galaxies live in groups, or that you are more sensitive to absorbers in groups for some?
Yeah, that was one of the questions I tried to pose here. So we know that when we look at the whole sky catalogs of galaxies, the group fraction is not such a high number. Actually, I compared the fraction of the groups I'm seeing here to I think it was like 30% is a field galaxies group fraction, and here it's more than 50. So it seems like we are biased towards the groups. And here my question would be here, is because there is some gas coming from the interaction between the members, which makes it more easy to actually have an absorber, or is it some other reason?
Yeah. Okay. Yeah, thanks.
Okay, I see a live hand of Michał Szymański rising. Michał, please.
I have a question regarding the same slide. This is 300 kiloparsecs. Is it, do you mean the impact parameter this high?
Yes.
So is there any gas, absorbing gas that far away from the center of galaxy possible?
Yes, actually it is. We expect to sometimes to see the gas up to the 1 megaparsec from the galaxy. Even this very high ionized gas can expand so far away. And 300 kiloparsec per Milky Way like galaxy is the radial viral radius. So we still are in the sphere of influence of the galaxy actually. So yeah.
Thanks.
Okay, any more questions? I have one related to your HST images you showed, that the galaxy and the quasar, they're very close to one another, right? So I was wondering, first I was wondering how Gaia would be useful for you. You know, Gaia measures the astrometry of quasars, and there are thousands of quasars which have non-zero parallaxes in Gaia, and people wonder why. And one of the reasons is that they could be blended with something very close, right? So, and probably even Gaia cannot resolve them. In some cases, maybe Gaia can. So maybe that would be a useful information for you if you don't have HST image. But my other question is actually, what if the galaxy in front is so close in line of sight that it actually lenses the quasar? Do you have cases like this, or do you take that into account? The lensing of the quasar.
We have cases like that. They're very rare, but this is the best because it gives us several sightlines.
Exactly.
Yes. So the other girl from our group, Ramona, she's working on lensed quasars, and she has several cases like this where at least she has like 4 images. And what we can see is that, let's say, if you have 4 images of the quasar, then we can see absorption differs in between the images, giving us an information about the spatial extent of the clouds of gas. Yes, and people also using the arcs, which are not lensed by the galaxy in question, but just lensed. And then some absorption is coming through in front of those very elongated lensed quasars or galaxies, and that gives you even better information about the spatial extent. So yes, this is there are not many sources like this where we actually see absorption towards those quasars which are lensed, but when we do, it's very important because it gives us more than one sightline. through the halo.
Cool. There is a group Matt Auger is involved in, you know him from Cambridge, and they've been using HST images, but also recently Gaia as well, to identify candidates for lensed quasars in that way, so that they are so close that they are not resolvable, but then when they see with HST images, they can resolve them. So I guess these would be ideal cases for you to study, right?
Yeah, I have to look into that then, definitely.
Okay,
we are
great.
mostly using the so far from DES in terms of looking for lenses, but I guess Gaia can give us much more information on that.
Okay, any more questions to Alex? There is one more from Michał Michalski, please.
I can ask another one about the slide you showed at the beginning with the, I believe it was MUSE deep field, the stacked image of Lyman alpha emission. Yeah, that one. So my first question is why we are not doing that always? Is it because it's more expensive? Because you can see the intergalactic medium gas here in emission, but probably you cannot do that very efficiently. And the second, the gas distribution looks very uniform here. Is this just, I don't know, some resolution problem or some integration along large redshift range? Or I would expect to be the gas density in the intergalactic medium to be very variable. Like close to the galaxies would be a lot, and then.
Okay, so I'll answer the first question. I think this is 150 hours with MUSE.
Yeah. Okay.
So I think that answers the question. Yes, it's very it's very heavy observationally, and we cannot really use MUSE to do this. We hope that with ELT that will go down to many less hours, and we can start to look not at the stack like this, but at the single galaxy halo. But in terms of how that looks, this is the integrated view over between redshift 2 and 4. So we are losing all of the information about the third dimensions. It's just a stack over all of those redshifts. I think that's why you don't see any structure here. Okay. In this paper, this is a Nature paper, they are looking into different halos profiles of the galaxies at different redshifts. And then they definitely see what you just said to expect, the fall down going away from galaxies. But here is just a stack of everything. So.
Okay, thanks.
Okay, great. I don't see any more questions. So let's thank Alex again. I'll do the clapping on behalf of
everyone. There is one on YouTube.
Sorry?
There is one question on the YouTube channel.
Oh.
Don't have it open. Could you please read it, Michał?
Yes. How does the metallicity in the circumgalactic medium for relatively nearby galaxies compare with those observed when star formation rates were highest, around 10 billion light years ago?
Oh, okay. Well, this also it's a difficult thing to measure because the further we go with redshift, we start to lose metal lines. We cannot observe them anymore, or they are also very faint. And then also the other thing is that the metallicity goes very way down in general in the universe. So we expect much lower metallicities and much less enrichment in this material than we see in a redshift one. I cannot say the exact number, how many decks we are talking about, but the higher redshift we look at, the lower we have less metals in the absorbers and in general in the universe. So yeah, I don't know if that answers well, but
I don't know either.
Well, I hope.
Thank you. And sorry, I missed this. I didn't open the YouTube stream. Okay, I don't see any more questions. So let's, I'll thank Alex again, and thank you all for joining. We had almost 40 people watching it live, and I hope there will be more watching it, the recording on YouTube, which will be available soon after we finish. Before we conclude, I would like to say that if you're welcome, everyone is welcome to stay a bit longer after this seminar finishes. So for less formal conversation, normally we would go to a pub or something, but here we have to stay with Zoom. So and I invite you for the next week's seminar. We will have 2 talks about Gaia. Especially about the new Gaia data release. So welcome next week. Join us next week. And thank you all for joining today. And I stop everything now.